Hello dear students, I Dr. Bindiya Sharma once again welcome you to the third video lecture on spectroscopy. In the last lecture, we have studied the principle of UV spectroscopy. In this lecture, we'll see the instrumentation and application of UV spectroscopy. So let's start. Now, depending upon the monochromators which are used, the instrument is classified as photometer or spectrophotometer. Spectrophotometer is able to detect the percentage transmittance of light radiation whenever the light of certain intensity and frequency is passed through the sample. It can be of two types, single beam spectrophotometer or double beam spectrophotometer. The instruments for measuring the absorption of UV or visible radiation are generally made up of the following common components. First is a suitable source of radiation. If we want to use UV, we need to have the source of radiation for ultraviolet, and if we want to use for visible, we need to have a visible radiation source. Then a system comprising of lens, mirrors, slits, which will be focusing the beam on the sample. And then we need a monochromator system. Then we also need a sample holder, which is generally called as cell or a cuvette, in order to keep the sample. And finally, we require a detector system, which will be able to detect and record and give us the spectrum. So here is the single beam and double beam spectrophotometer. We can see in this that single beam spectrophotometer has a light source, and which is a polychromatic light. And then we have got a monochromator system. This monochromator is capable of again selecting this, converting this polychromatic light into monochromatic radiation or light. This monochromatic light or radiation falls on the sample. Some of the intensity is being absorbed, and we can calculate it by this Beer-Lambert law. And the transmitted radiation is detected by the help of this detector. And finally, the computerized, by using a computer, will get a chart, or we can say we'll get a UV spectrum. This here, we are using single beam, and the same single beam is passed on the sample. So this is termed as single beam spectrophotometer. But there are double beam spectrophotometers also, which are better than single beam because they give better results. How they are working? They're working in the similar manner as single beam, but see, we have got a light source that is polychromatic radiation, and this monochromator will convert this polychromatic into monochromatic radiation. Here the difference is that this monochromatic radiation, by making use of a beam chopper, we'll be dividing this radiation into two beams of equal intensity. The one beam will be again passing through the sample, which will be kept in the cuvette, and the second beam will be passing through the reference cuvette or the reference. Suppose generally the reference is made of solvent, like suppose we are having a sample, we have dissolved it in a particular solvent, so the same solvent will be used as a reference. So what will happen is this sample will be absorbing some radiation, and this reference also will be absorbing some radiations, and will get a transmitted radiation for the sample as well as the transmitted radiation for the reference. This detector will compare both the transmitted radiation from the sample and from the reference, and then we'll get a spectrum of UV spectrum. So this UV spectrum will be having better results, or will be more authentic spectrum as compared to the single beam, because single beam it has got no such comparison with the reference, but here we can have the reference. So the amount, the solvent which was there, in which the sample was dissolved, the absorbance of the solvent is being again here is being measured and thus detected. But here both absorbance of sample as well as the solvent is taking place because it is a single beam. So we get better results by using double beam spectrophotometer. Now single beam spectrophotometer, same, we are having a light source, and again which will be keeping the sample in the cell or the cuvette, then the light will be passed, and finally with the help of a detector, we'll be able to detect and measure. The amplifier will be there, which will amplify the message given by the detector, and finally it will be recorded in the form of a UV spectrum. Now double beam spectrum, the same thing, like double beam by the help of a chopper, which is a device which will again split the monochromatic beam into two beams of equal intensity, and then the light beam passes through a slit. We have an entrance slit and then exit slit, and it hits a diffraction grating or the prism. The grating can be, or the prism can be rotated, and for a specific wavelength which we need to select, and then that specific monochromatic single wavelength which is being selected, again it will pass through the sample by the exit slit, and then the absorbance will be measured by the detector. The same double beam spectrophotometer is shown here. So here we can see that this is the light source, this is the slit number 1, this is the diffraction grating which will convert this light, and monochromatic radiation will be passed here, and this is the chopper which is going to divide this into two halves. See here, with the help of mirrors we are doing it. So this is the reference beam passing through the reference cuvette or the cell, and this is the second beam or the sample beam which is passing through the sample cuvette, and here here are the two detectors, separate detectors for the reference as well as for the sample, and we'll be getting a UV spectrum after comparison of this reference beam as well as the sample beam. Now the procedure is very simple. We need to first fill the cuvette, and then we need to place the cuvette. The wavelength has to be set, and then we need to calibrate the curve. Spectrophotometer's range has to be observed, and if the absorbance values of the sample are outside the range, then we need to again dilute the sample. And then finally the absorbance or lambda max value is being calculated by using the Beer-Lambert law. And then there are various things which are there uh, in order to make a double beam spectrophotometer. There are different parts of a double beam spectrophotometer. So let us see the different parts which comprises the double beam spectrophotometer or spectrophotometer. So the common parts are, first is the source of radiation. We need to have the radiation source. So the radiation source, how it should be, the radiation source should be a continuous radiation which will be covering the entire wavelength, and the radiation source involves the formation of excited molecular species, which we know. Because of this radiation only, the entire principle of UV is based. That is, what happens is this UV ultraviolet radiation is being absorbed, and the electronic transition takes place from the electrons transmits from ground state or the lower energy state to the higher energy state by absorbing a particular UV radiation. So this is the basis of this. Radiation source needs to be selected, and there are few requirements of the radiation source. That is, the radiation source should be stable, it should not fluctuate, and it should have incident light of sufficient intensity. It should emit continuous spectrum of uniform intensity. It should not show any kind of fatigue when we are using it continuously. So radiation sources are of various types. Means we can use various different types of radiation sources by the help of deuterium lamp, hydrogen lamp, tungsten lamp, xenon discharge lamp, mercury arc lamp. These all 5 types of radiation source, if we want to use, we can use it for ultraviolet radiation. That is, whenever we are using deuterium, hydrogen, tungsten, xenon or mercury arc lamp, we get ultraviolet radiation. For visible radiation, there are separate radiation sources like tungsten lamp, mercury vapor lamp, and carbonon lamp. Let us see few of these radiation sources. First of all, tungsten lamp. This tungsten lamp is similar to that of the electric light bulb which we are using at our homes. So it is a tungsten filament inside the bulb which is heated electrically to produce the white heat, and then the intensity at short wavelength is small. So these lamps are stable and very easy to use. Second comes the hydrogen discharge lamp. These lamps, in these lamps, the hydrogen gas is stored at high pressure, and whenever electric discharge is passed through the lamp, the hydrogen molecules will be excited and they will start emitting the ultraviolet radiation. Both the deuterium and hydrogen lamps emit a radiation range in the range of 160 to 375 nanometers. They are also stable and more widely used. Now, deuterium lamp, if deuterium is used in place of hydrogen, if we replace hydrogen by deuterium, then the intensity which is emitted is 3 to 5 times higher as compared to hydrogen. So obviously it is more expensive also as compared to the hydrogen lamp, but it is not commonly used, but it is used only when a high intensity is required. So next is xenon discharge lamp. Here xenon gas is again stored under high pressure, and next comes the mercury arc lamp. Here mercury vapor is stored under high pressure and it is not suitable for getting the continuous spectral lines or the radiations, but generally pressure mercury arc is very useful for calibration purpose. Now next part is mirrors. So mirrors are used to reflect, to focus, to collimate the light beams to the spectrophoto in the spectrophotometer. So mirrors play a very important role in the spectrophotometers. And then there are two types of mirrors basically. One is cornus type or refractive type, and the other is littromirror or the reflective type. In the cornus type, it has optical angle at 60 degree, whereas in the litro type, it has optical angle at 30 degree. And here, next part is known as monochromators or filters. So monochromators are used for selecting the narrow band of wavelength. It is used to isolate the radiation of the desired wavelength from the continuous spectra, because what happens is from the radiation source we'll be getting the continuous spectra, but we don't want that continuous spectra. At a time we want a single wavelength radiation only, that is monochromatic radiation, and for this purpose monochromators or filters are being used. Monochromators consist of various components or parts such as entrance slit, a collimating lens, and then a dispersing device which is generally a prism or a grating, and we again have focusing lenses for completing the focus, and then we have the exit slit. So slit is an important device here because in resolving the polychromatic radiation into monochromatic radiation. So we have two types of slits here. One is entrance slit and the other is exit slit. So polychromatic radiation, it enters the monochromator through the entrance slit, and then it strikes the dispersing element at an angle, that is the prism or grating. Here the beam is split into its components, and after that finally it passes out through the exit slit, and we get a particular wavelength radiation, and then that radiation is let to fall upon the sample which is kept in a cell or the cuvette. So again, for monochromator, we have got two different types or the choices. We can make use of prism or we can use a diffraction grating. So we are all well aware of the prism. It is made of glass, quartz or fused silica. Whenever white light is passed through the prism, the dispersion of the polychromatic light in the different rainbow occurs. That is, vigor takes place. So this is very well explained by this diagram. Next is grating. So grating are better as compared to the prism. They are more effective, one, in converting the polychromatic light into monochromatic light because they have got better resolution. So what happens is these rays falls on the reflecting grating, whereupon the different wavelengths are reflected at different angles. Gratings are basically of two types: diffraction grating and transmission grating. We can see from this figure that this is the entrance slit and this is the set of mirrors, and this is the grating which is being used here, and then a particular monochromatic radiation is let to pass on by this exit slit. Now we have this sample holders also. So where to keep the sample, where to hold the sample? So we have got cells or cuvettes, which are generally rectangular or cylindrical in shape, which are used to handle or keep the liquid samples. They should be transparent to the wavelength in whichever region we are recording. Like suppose if we are using ultraviolet radiation, they should be transparent to ultraviolet. If we are using visible radiation, they should be transparent to the visible radiation. And they should be made of such a material which should not absorb that particular wavelength. It should not happen that if we are using ultraviolet radiation, the material of the cell or the cuvette should not be such that it also tends to absorb the ultraviolet or visible radiation. Otherwise, we won't get the proper and the correct absorbance by the sample, our sample. So quartz cuvette can be used because glass tends to absorb wavelength less than 350 nanometers. So choice of the sample cell, again, it is based on the path length, shape, size, transmission characteristic. And the cells can be of any shape. It can be of rectangular or cylindrical of generally 1 centimeter thickness. And we have to keep these cells very clean. No fingerprints or blotches should be present on the cells. Then next is detectors. So we have to see the various types of detectors which are being used, because the detectors play a very important role. See the radiations which are being let to fall upon the sample, and the sample tends to absorb the radiation, and some of the incident radiation it gets absorbed, and few of it gets transmitted out. But how much absorbance is taking place and how much is the transmitted radiation, how we need to detect? We will take the help of the detectors in order to detect the transmitted radiation, or in order to check the absorbance done by the sample. So detectors are the devices which converts the light energy into the electrical signals that are displayed on the devices. So we have types of various types of detectors, but the most common and the important detectors used are the barrier layer cells or the photovoltaic cells. Next is phototubes or photoemissive tube, and the last is photomultiplier tube. So there are some requirements of the detector. It should give a quantitative response. It should have very high sensitivity. It should have the short response time. It should not take much of the time to give the spectrum. Now, we'll see one by one all the three types of detectors. The first is the barrier layer, or we call it as photovoltaic cell or the phototronic cell. Now, for this consists of a metallic base plate like iron or aluminium, which act as one of the electrode. And then we have a thin layer of semiconductor material deposited over it. You can see in the diagram. And then the surface of this selenium, like selenium as a semiconductor used here, the selenium is covered by a thin layer of again a silver or gold, which act as the second collector tube. So when the radiation is incident upon the selenium, the electrons are generated and the electrons are collected by the silver. This accumulation at the silver creates an electric voltage difference between the silver and the cell. So what happens? This is being measured, and finally we get a signal. So this is the how the barrier layer detector works. Next is the phototubes, or we also call it as photoemissive cells. A phototube consists of an evacuated glass bulb. There is a light sensitive cathode inside it, which is coated with a light sensitive layer such as potassium oxide and silver oxide. It is more sensitive as compared to the first one, that is the barrier layer cell, and it is most commonly used. When the radiation is incident upon the cathode, the photoelectrons are emitted, which are again collected by the anode. So then these are retained by external circuit, and then the current which is being produced is amplified, as well as it is recorded. So this is how the photo multiplier tube, phototubes works. The third one is photo multiplier tube. So this is a commonly used detector in case of UV spectroscopy. It consists of a photoemissive cathode, and it has several diodes The diodes emit several electrons for each electron striking them, and it has an anode also. The photon of radiation entering the tube strikes the cathode first, causing the emission of several electrons. These electrons are accelerated towards one by one dynode. Let us say they are accelerated towards the first dynode. So these electrons are accelerated towards the after first dynode to the second dynode. Like suppose in first dynode, which is 90 volt, are more positive than the cathode. These electrons are accelerated from first dynode to the second dynode to produce more and more electrons. Eventually, the electrons are finally collected at the anode. And by this time, each original photon has produced approximately 106 to 107 electrons by the time it reaches the anode. And finally, what happens is the current is amplified and measured, and the photomultipliers are termed as very sensitive towards the ultraviolet and visible radiation, and they're very quick in giving response. So this is how the photomultiplier tube works. This is the incoming photon, and this is the dynode, one by one dynode, second dynode, third dynode, and finally this is the anode. We can see the number of electrons are increasing as it passes on from one dynode to other, and finally we get the current, and which is being amplified and thus recorded. Now let us see one simple like UV spectrum sample. So how this UV spectrum looks like. This is the absorbance which is being plotted against the wavelength, and this is how a broad peak is being observed. Here we are using the term lambda max. See, this is how this is calculated. The maximum lambda max gives the wavelength where the maximum absorbance or the absorption occurs. So why we are having the broad peak, I hope you understand now, because the transition is taking place from one electronic level to other, but in between we have got vibrational and rotational levels also. So this is how a sample UV spectrum looks like. Now let's see few applications, important applications of UV visible spectroscopy. So the very first application of UV visible spectroscopy is we can detect the impurities present in the organic molecules, because we will be getting additional peaks if some kind of impurity is there in the sample. The additional peaks which will be indicated in the spectrum, by studying those peaks we can check the impurities which are present in the molecules or the compound. The structure can be easily detected for the organic compounds by using the UV spectroscopy. So this is the next application for the UV visible spectroscopy, that if we want to study the structure of, if we want to detect the structure, so this is an important spectroscopic technique which can be used to study the structure of organic molecule for the presence or absence of unsaturation, that is a double bond presence or absence. The presence or absence of heteroatoms also can be studied by studying the lambda max value or the peaks. Third important application is the study of chemical kinetics. We can also study the chemical kinetics of a reaction by using this spectroscopy. The very important application is the quantitative analysis. The UV absorption spectroscopy can be used for quantitative determination of compounds that absorb UV radiation, and this determination again is based on Beer-Lambert's law, which we have already studied. The next important application is the qualitative analysis. The UV absorption spectroscopy can characterize those type of compounds which absorb UV radiation. So identification can be done by comparing the absorption spectrum with the known. That is, if we have got some unknown sample, so if we compare it with the already present spectra of the known compound, and if it matches, we can easily check out that which is the unknown sample, and we can identify the compound. As well as next application indicates that we can also calculate dissociation constant of acid and bases using the formula pH is equal to pKa plus log A minus upon HA. So pKa value can be easily calculated if the ratio of HA A minus upon HA is known at a particular pH. Then next is the quantitative analysis of pharmaceutical substances. There are many drugs which are either in the raw form or in the form of formulation. So if we want to assess any kind of drugs undergoing, which is in undergoing process of the formation, it can be easily analyzed. Last application is the molecular weight determination. It is again an important application. The molecular weight of the compounds can be easily measured by this UV spectrophotometry, but mostly it is done by mass spectrometry. But by using UV visible also it can be done. But what we need to do is we need to convert it first into some other compound. Like for example, if we want to determine the molecular weight of an amine, we need to convert it into amine picrate, and then the known concentration of amine picrate is dissolved in 1 liter of the solution, and its optical density is measured, which we get at lambda max value at 380 nanometer. And after this, after getting this result, then the concentration of the solution in gram moles per liter can be calculated using the formula which is used to calculate the molecular weight determination. So this is all about the instrumentation and application of UV and visible spectrophotometry. With this, we complete this topic of UV, ultraviolet visible spectroscopy. We have seen the principle, we have seen the instrumentation and various applications. Hope you have been benefited and gained knowledge about the topic. Thank you and happy learning.